Hello, all. This is Mr. G, and welcome to Beating the State Test Round 5 Exponential Functions and Expressions. In this video, we're going to be going over all of the released items, the released questions from the most recent round of state tests that have to do with exponential functions and expressions. So, what do we need to know about these topics before we jump into these questions? If we're talking about exponential expressions, we need to remember our basic exponent rules. So, like for example, if we have a negative exponent, that means rewrite it as a fraction. So if the negative exponent is in the numerator, we move it to the denominator and change it to a positive power. And likewise, if we had started with a negative exponent in the denominator, that means move it to the numerator and make the power positive. Another rule we need to remember is if we're multiplying common bases, then we add our powers. So x squared times x to the third would be x to the fifth. Essentially, 2 plus 3 gives us 5, since we have a common base of x. And if we're dividing common bases, then we subtract the powers. So here, 3 minus 2 would be x to the first power as our final answer. Another thing we need to be able to deal with is a rational exponent, essentially an exponent that is a fraction. Now, in case you've never seen this before, it's actually not that bad. The denominator in the power essentially needs to get turned into an index of a root. So if we see a denominator of 2, that just means we're talking about the square root of something. And we're talking about the square root of x to whatever the numerator is. So if we're going from a rational exponent to a radical expression, the denominator becomes the index and the numerator becomes the power inside that root. So that takes care of exponential expressions, but what about exponential functions? There's really two main categories of exponential functions. We've got exponential growth and we've got exponential decay. Growth obviously is getting bigger, decay is obviously getting smaller. If we're looking at the graphs of these two functions, they're going to look pretty different. Growth is going to be going up faster and faster, and decay is going to be going down, decreasing slower and slower. So it's two very different pictures for these functions. When we're talking about the equation, they actually both start with the same general form. F of x equals a times b to the x. Now a is what we call our initial value, which is essentially is the y-intercept. So for growth, our a value would be right here, and for decay, our a value would be right there. A is always on the y-axis. It's the y-intercept after all. B is slightly more complicated because B is either the growth factor or it's the decay factor. Either the growth factor or the decay factor. And how we calculate this b value changes depending on whether it's exponential growth or decay. If it's exponential growth, it's going to be b equals 1 plus r, where r is the rate of increase. And if it's exponential decay, it's going to be b equals 1 minus r, where r is the rate of decrease. The reason both of these equations start with a 1 is because that 1 represents 100% of our initial value. And then if it's exponential growth, we add on whatever the rate of increase is. And if it's exponential decay, we subtract whatever the rate of decrease is. So that's everything we need to know. Let's jump right into the problems. Number 1, which is a calculator problem. It says the functions h of d, g of y, and f of m each represent the balance of a savings account that is opened with an initial balance of $8 with no additional deposits or withdrawals. F of m equals a times 1.0008 to the m, where m is the number of months since the account was opened. G of y equals a times 1.01 to the y, where y is the number of years since the account was opened. And h of d equals a times 1.00005 to the d, where d is the number of days since the account was opened. And then it says if the time period is the same for all three accounts, we have to order the functions from greatest to least growth rate. So they're essentially asking us to put them in order for how fast they're going to grow if the time period is the same, because each of these right now are growing over different time periods. F of m is being calculated for months, g of y is being calculated for years, and h of d is being calculated for number of days. It doesn't say what the time period needs to be, it just says that the time period must be the same. So let's pick a time period that's going to be easy for us to calculate. Let's just calculate all these for 1 year and then compare how much they've grown. Let's start with f of m. So m is the number of months, so that means we're going to plug in a 12 to get it to 1 year. So that would be a times 1.1230 to the 8 and to the 12th for number of months. And we can type that right into a calculator. Let's turn the calculator on. It's going to be 1.1230, 8 to the 12th. And that gives us a growth rate of 1 point, well, let's see, it's going to be a times 1.0096. We'll round it to 1, 2, 3, 4 places. G of y is going to be really easy because it's 1 year, so it's just going to be a times 1.01 to the first power, which is just going to be a times 1.01. And then for h of d, it's going to be a times 1 point, how many zeros is that? 1, 2, 3, 4, then 5 to the d. Well, let's think. If it's number of days to get to 1 year, it needs to be 365 as the exponent. So we just type that in the calculator. 1.1234 zeros, then a 5 to the power of 365, which comes out to a times 1.0184. It rounds to. Now we just have to put these in order from greatest to least growth rate. Let's see. So which one of these had the biggest growth rate? Well, it's h of d because 1.018 is bigger than 1.01. So let's put that one first. So that was h of d, that goes first. And then let's see, which one is in second place? Well, that's this one, 1.01, which is bigger than 1.00. So that's g of y. So g of y is second. And then f of m is going to be third. Now we just compare that to the answer. And we got it correct. Excellent. Number 2. It says the size of the population of a certain city was 25,000 in 2010 and decreased 4% each year afterward. Part A. The size of the population y can be modeled by an exponential function of the form y equals a times b to the x, where x represents the number of years since 2010, and a and b are constants. What is the value of b? So they're not asking us for the entire equation here. All they're asking us for is b. And we remember that b is either the growth factor or the decay factor. And since they're talking about a decrease of 4% each year, that makes b the decay factor, which we calculate using b equals 1 minus r, where r is the rate of decrease. So this is just going to be 1 minus, what's the rate? 4%. Now you don't want to make the mistake of writing 1 minus 4, because remember, this 1 represents 100%. So we have to change this 4% into a decimal and make it 0.04. And 1 minus 0.04, that just comes out to 0.96. And that's our answer. We check it, and we're correct. Number 2, part B. Suppose the equation representing the size of the population is graphed in the xy coordinate plane. Which statement is true? Let's take these statements one by one. A says the size of the population in 2010 is indicated by the x-intercept. Well, I guess we could graph this and try and figure it out, but let's just think about it. If we have a graph, the x-intercept obviously is going to be somewhere on the x-intercept. I'm just going to pick one. Well, this doesn't make any sense because the x-intercept is when the y value, essentially the population at this point, would be 0. So since the x-intercept is when the population is going to be 0, we know that's not going to be the population in 2010, so A is not a choice we want to pick. B says the size of the population in 2010 is indicated by the y-intercept. So the y-intercept is going to be somewhere on the y-axis. Maybe it's right there. I'm just picking a point. And if we remember, that's our a value, our initial value, when we're using the general form a times b to the x, the general form of an exponential function, I should say. So I'm pretty sure that's going to be the answer. Let's take a look at C and D just to be on the safe side. Both of these are talking about the rate of change per year. C says it's indicated by the x-intercept, and D says it's indicated by the y-intercept. Now, both of these sound really wrong because the x-intercept is going to be when the population is 0, not the rate of change, and the y-intercept is the initial value. It's not the rate of change, but we can even be more sure of this because they're talking about the rate of change of an exponential decay function. And if we know anything about exponential growth or decay, is that the rate of change is constantly changing. It's not going to be a linear function, so C and D are incorrect, B should be our final answer, and it's correct. Excellent. Number three, which expressions are equivalent to the given expression for all positive values of x, y, and z? And they give us this expression and a bunch of choices, and we have to figure out which one of these matches this original expression. Before I even look at these choices, I'm going to try and do some simplifying here to make this look nicer. Well, let's see. Let's deal with the x's first. So it's x squared divided by x to the negative fourth. Well, we remember this negative exponent is going to take that base of x and move it up to the numerator. So we could rewrite the x's here as both being in the numerator, and it's x squared times x to the positive fourth. And then, okay, we're multiplying common bases here, so we can add the powers and get x to the sixth in the numerator. Now let's take a look at the y's and see what's going on there. All right, the exponents are both positive, so it's y to the third divided by y squared. Well, we're subtracting here, so we can just do 5 minus 3 and get y squared in the denominator, because essentially 3y's or 3 powers of y cancel out from both of them, leaving 2 powers of y remaining in the denominator. Now let's take a look at the common base of the variable z. And the first thing I notice is that we have a rational exponent here. So I'm going to rewrite both of these powers with a common denominator. So in the numerator, I'm just going to leave it as a power of 5 over 2. And in the denominator, I'm going to rewrite it as z to the power of 4 over 2, because 4 divided by 2 is the same thing as 2. And now that we have our common denominator, we can just subtract here. So 5 over 2, take away 4 over 2, well, that's z to the 1/2, and it's in the numerator, because that's where the bigger power was. The bigger power was 5 over 2, and that was in the numerator, so that's where our answer goes after we subtract. Now that we've simplified the expression, all we need to do is take a look at the choices and figure out which one of these match our answer. Let's take a look at A first. It says x to the sixth, which is good, times y squared, which is not good because y squared should be in the denominator. So we can skip A. It's not correct. Looking at B, it says x to the sixth, which is good. And then it says y to the negative second, which is the same thing as y squared in the denominator. So far, so good, times z to the 1/2. So yeah, this is exactly the same thing, because I could rewrite this as this y to the negative second as a y to the positive second in the denominator. That's how negative exponents work. So we found one answer. C is going to be immediately incorrect because it says x to the negative eighth, and that's not the power of x we're looking for. Oh, I guess they were hoping we would accidentally multiply the 2 and the negative 4 or something like that, but we didn't fall for that trap, so we just skip it and move on to D, which is exactly what we have for the answer. So that's going to be our second choice. It says select all that apply, which is why we're going through all of them. Then we've got x to the sixth, which is good, y to the negative second, which is the same thing as y to the positive second in the denominator, and then we've got the square root of z, which is the same thing as z to the 1/2. Because remember, when we have a rational exponent, we can rewrite that as a root where the denominator is the index and the power, excuse me, the numerator becomes the power of the base, the power of the z in this case. And okay, don't get confused that there's no index there. Remember, whenever there's an index of 2, we usually don't even write it and we just leave it as an invisible 2. So E is another correct answer. Let's check out F though. It says y to the 15th. Okay, that's nowhere near correct. Oh yeah, again, they're hoping we're going to multiply there, but we're not falling for that. Last but not least, we check on G, which is x to the 6th. So far, so good. And then the square root of z to the 5th. That is not correct because the numerator should be a 1 there. So G is wrong. So the answer is B, D, and E. Let's check it. All right, excellent. And this video is finished. As always, thank you for watching. If you have questions, let me know. Enjoy the rest of your day.